Hi everybody, so in video 2128 I burbled on about these things. These are the electro smog paints that are making a splash in the market at the moment, and you're suddenly finding a whole load of these things around. Now I got some Rustin's G Shield. I paid £12 for this 125ml tin, but I'm not recommending them. It's just the first one I've got to have a play around with, and the resistivity of this is 10 ohms per square for a 100 micrometer coat. I mean, that's not bad. It's not brilliant, but it's not bad. And it means that we could use this for, well, all kinds of things. And that's what I'm excited about. Now, I used to make this ink myself and we had 1 ohm per square. But I can tell you, for 25 micrometers, it was an absolute pain to make. And since we've moved, of course, I don't make it anymore. So finding one on the market that was basically bulk buyable means that it's a possibility of doing some very exciting things with it that may actually turn into products. So things like underfloor heating. And the thing I'm really interested in at the moment is generation, particularly thermoelectric generation. Thermoelectric generators are fascinating devices that convert heat into electrical energy through a principle called the Seebeck effect. This technology harnesses the temperature difference between two dissimilar conducting materials to generate electricity. And as a concept, it has immense potential for various applications, from powering space probes to enhancing energy efficiency on Earth. At the core of a thermoelectric generator lies the Seebeck effect. It was discovered by Thomas Johann Seebeck in the early 19th century, and it relies on a phenomenon that when a temperature gradient is applied across a junction of two different conductors, it induces a voltage difference and, consequently, an electric current. The fundamental components of a TEG consist of thermocouples made of two different materials. They're often semiconductors like bismuth telluride or lead telluride. When one side of these thermocouples is heated while the other remains cooler, a voltage is generated across the junction due to the temperature gradient. The issue with things like bismuth and lead is they're not very nice, a bit difficult to handle and a bit more expensive. But there do exist a whole range of conductive materials that can be used, including things like graphite and zinc, graphite and aluminium, graphite and bronze, graphite and copper. You might be getting a theme here. A lot of them use graphite, and of course in these electro smog paints they tend to be graphite. Rustin's is advertising itself as naturally exfoliated graphite, whatever that is. Now, TEGs find applications in various domains due to their unique advantages. In space exploration, for instance, they power probes and satellites where solar energy isn't available, converting the heat from radioactive decay, or the temperature difference between the spacecraft and the surrounding space, into electricity. They're also employed in remote locations where access to conventional power sources is limited or impractical. They play a role in waste heat recovery in industries and automotive sectors, where the substantial amounts of heat generated during operations are normally wasted, but thermoelectric generators can convert this waste heat into useful electricity, significantly improving energy efficiency and reducing environmental impact. One of the key advantages of TEGs is their reliability and longevity. Unlike conventional power sources that require moving parts or chemical reactions, TEGs have no moving parts. They don't have chemical reactions, and this results in lower maintenance and much longer lifespans. It's a characteristic that makes them ideal for applications in harsh environments or locations where maintenance is difficult. However, challenges do persist in enhancing the efficiency of TEGs. The conversion efficiency of these generators is much lower compared to other power generations, and that limits their widespread adoption. But very significantly, cost remains a significant factor inhibiting the broader use of TEGs. Materials used in high-efficiency thermoelectric modules can be expensive, and that impacts the overall cost-effectiveness of the generators. In generation, cost effectiveness is king. It's all about the pounds per kilowatt hour you produce. And if you can come across a method which substantially reduces the cost of TEGs as a proposition, then clearly you're on a bit of a winner. So to my mind, looking at thermoelectric generators is a very worthwhile proposition, particularly if the cost of materials is so low that the cost of generation goes into your boots. And of course, that's what's attractive about graphite and carbons. And they have been producing thermoelectric generators of nothing but graphite. But to give this one a go, what I thought I'd do is do a thermoelectric generator that's a combined aluminium carbon generator. So there's graphite on this side, and I just painted a strip of the G-shield on there and stuck a bit of aluminium foil on there for no other reason than it's easy to do. I mean, we could experiment with things like zinc foil and things like nickel foil, and we could experiment with just having carbons. There's a whole host of things to do, but to demonstrate whether it works or not, I thought I'd just choose the simplest. So I've done this shape. You can see there's a long tail here of the G-shield. There's a bit of aluminium foil there. We're going to connect that to the positive and the negative, put some heat on it and see if we actually get any voltage or not. So let's clip it up. Now I can tell you that the ambient temperature at the moment is about 5 degrees. I'm cold, and I'm going to heat it with the hot from a hairdryer, and we're going to have a see if that does anything. So let me turn that round so you can have a look at it. We've got a voltage reading on there. Let's turn this on and see what happens. Awesome! So you can see that immediately we put a heat supply on it, we got an increase in the voltage. It was millivolts, but it was a dramatic increase. We took the heat away and it dropped, heat back on, and we got a voltage again. So this is working as a thermoelectric generator. Granted, one little point doesn't give you much, but what's good about something like this is you could print thousands of them for pennies. And if we have that on a wall, for instance, with that bit sticking out and this bit going into the house, on a few degrees difference, we could generate a substantial amount. Anyway, I wanted to share that with you because that is readily available, and £12 for a tin of it, I don't know how much that'll do, but a load of it. And it's really up to us to investigate it and see what we can come up with. I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.